So all of this has been a bit abstract. Let's look at the propagator in the position representation. So in the position representation, the state alpha looks like this, right? It is x, bra of x with the ket of alpha t, right? But what is alpha t? In terms of the initial condition, initial state, it's u, t minus t0, alpha of t0, right? So, and then what we can do is that we can insert a complete basis of states, position eigenstates. So I get d cubed of x prime. Here that's x, u, t minus t0, x prime ket, x prime bra, alpha of t0, right? So I'm just inserting the identity operator in terms of this and this. Is this okay? Is this clear?
Yes, sir.
Okay. So then we have d cubed of x prime. What is this thing? This is nothing but the wave function alpha at x prime at an earlier time, right? And this thing we define to be k, which is also known as a propagator, k x t x prime t0, okay? So this has a nice geometrical interpretation. So to understand the geometrical interpretation, let's consider, although we are in Newtonian space-time, let's consider the whole space-time as a four-manifold. So of course we have absolute time here, so we are not allowed to foliate this space-time in any way we like, but so time is going in that direction. So here its time is t0, and space is, say, going in these two directions, okay? So here what we have is a slice, a spatial slice. And so any point on this spatial slice is given by a 3 vector x prime, okay? And now in the future, we have, similarly, at time t, our three-dimensional space. Okay. And what this equation is telling us is that, suppose we know what the wave function looks like at t equals 0 over all of space. Okay? And then what's happening is that we want to know in the future what happens, say, to a particular value of x at time t. So let this be time t. So what does causality tell us? Causality tells us that, these initial condition is going to propagate at some speed, and the speed will be given by the energy of the particle, right? It'll depend on the system. And this propagation, as you can see at this point, the influence will come from many points in the past, right? Is that clear?
Yes, sir.
Yeah. And that's exactly what this integral is saying. This integral is saying that to find okay, on the left-hand side, we have alpha x at t. What it's saying is that the value of the wave function at some point x time t is going to be dependent on the value of the wave function at a past time, but at all points. But how that initial condition is going to propagate will be determined by this. Okay? So in a sense, what this is doing, what the propagator is doing, it's propagating the disturbance into the future for a unit wave function. So because this is a weighted integral, right? You can think of this as a weighted integral. This is the weight. You can think of this as the weight. So this is a weighted integral. And what this is saying is that it is telling us how much of the weight should be attached to a particular point in the past. So to make this more precise, let me take the initial wave function alpha x prime t0 to be a delta function. Okay, so then if I plug this into this equation, then what do I get? I get that the wave function in the future is xt is nothing but k xt x prime 0 t0. Okay, so this is basically what I'm saying. If, for example, the initial wave function was concentrated at one point, right? Then the wave function in the future is exactly the propagator, which is, it justifies my statement that the propagator is the, it propagates the influence of a unit wave function.